Dr. Khaled sent you this presentation. Did he present it in front of you? When? Oh. Did he explain it to you? Okay, this is his presentation, so let us review it, okay? In this presentation, he is summarizing a short summary of the project. He started by demonstrating the graphical user interface. If you are, can you see it clearly? Okay, okay. He started by showing you the graphical user interface. Like most of the hydrological software, you will have a panel for the layers and panel for the icons and tools besides the menus. Okay, this software, the user face of this software has something special, which is the graphical user interface is changing according to what are you doing currently. For example, when you start to add or insert data, the user interface will be modified automatically to support you with the tools for this purpose. And when you start, for example, simulating, another toolbars will be appeared and others will be disappeared. I mean, it always modify itself to provide you with the required tools and buttons. Okay. Of course, this is open. Okay. The data you have to use is, of course, consists of, as we described earlier, raster data and vector data. The main raster data is the topography. You know why? For example, if you are studying, thank you. Thank you. It's not here trash. I want to throw those because when they came to and see this pen here, they think we have enough. Now they will see we have no pen. We said earlier, when you have a raster file, it means it is a matrix full of data. So usually, if you have a raster, it means if this raster covers certain area over the globe, it means every special place all over this area is covered with data. On the other side, if you have vector data, for example, let us assume you have a road like this, you have only data over this line, only. But this shape file, it has no data all over this area. Okay? Now, if you are trying to represent or simulate a terrain, sorry, a watershed, what you want indeed, if this is a watershed, if this is the watershed and the rainfall over it, you need every tiny pixel to be involved in the simulation. Can you imagine if this area is blank without data? Okay, so you will not be able to simulate anything, and you will not able to calculate the hydrograph at this point. That is why the main input for the WMS is a terrain file, which we call it DIM. Okay, you know it? Okay. So, as you see in the screen, and most of the geographic files, we call it a file, but indeed it consists of many files, like such as the shape file. Shape file, we say shape file of the road, but indeed when you have it in a disk or in a flash memory, you will see that it is number of files with the same name but different extensions. When WMS or any other GIS tool started to read this file, it reads the whole package, and if any one of those files is deleted, the whole package will not be able to work properly. Okay, that's why in this screen we can see, look, 1, 2, 3, 4 files with the same name. See, each one of those provide part of the information about the terrain, about the dam itself. But you have to know which one you have to select when you start, when you need to import the terrain into the project, into the software. You have to know which one of those. In case of them, in this case, the one you want to pick or select by WMS to open is the one which has the extension ASC, which is called ASCII file. Let me open it so we can press it. Okay. When WMS, when you start your project, you start usually after defining the projection, you have to go to open the terrain file. This is the main or the first step, which is here. It's called importing grid. Grid is a way of naming a matrix. Okay. So in this case, he was opening this file, which is .asc. When he just selects the file, automatically the machine knows the coordinates of the boundaries of this file. As we can see here, it is the north is 28 point something, and here is 28.1. Okay. Do you think these values are geographic or projected? Look to the numbers. Who think these numbers, this file follows the geographic projection system, coordinate system? Who says this is geographic? Yes. Who says this is projected file? Yes. Okay. Do we remember what are the, of course we understand the difference between geographic and projected. Now we are asking about the numbers. You have to guess by looking at the number if it is geographic. We said that geographic coordinate system ranges between minus 180 to plus 180, which formulate the 360 degrees of the circle. But on the other side, the projection coordinate system starts by 0 at the Greenwich intersection with the equatorial and extends by the number of meters your place is far from that center point. So the number itself is much larger than the geographic one. Is it clear? So which coordinate system do you think this is one? I'm sorry. So these numbers are about 30. Do you think that place, which is, I think it is in Egypt, is 30 meters from the Greenwich line, or this is 30 degrees from the Greenwich line? It's degrees. So degree, not a meter. So is this a geographic or projected? Agree now? Geographic. Okay. Can you hear me? Don't you prefer to come closer? Okay. So now the WMS, when you start by opening the terrain dim file, it reads the boundaries of that file. It helps you to be just to check yourself if it is in the correct place or not. For example, in Egypt, we know these numbers are around our place. We live here in about 30 degrees, both longitudinal and circular. But for example, if you are working in China and you read these numbers, it means something is wrong. Okay. Also, you have a chance to edit these numbers. For example, according to the experience, if you know, you are studying that watershed, okay? And you know, this is a small watershed. Usually, we bring the demo files from the internet freely. So the files itself, maybe each file, when you need to download any file from the internet, you have to pick the boundaries. Usually, it may be 1 degree by 1 degree. Each file covers 1 degree by 1 degree. Some files maybe cover 5 degrees by 5 degrees. Or usually it is a square. Many websites provide you with downloadable data. You have to visit that website. There are many websites. They give you a map of the world. You start making zoom. You start zooming till you found the place you need to work on. Okay. ما احنا هنشتغل خلاص ايه هنشتغل ايه؟ خد امرك تقول لي اوسع ولا ما انا فاهم محتاجين منك شفت حاجه؟ كمان شويه ماشي كنا نقول ايه؟ Yes. Usually when you visit any website, you download it. It is 1 degree, 1 degree by 1 degree, maybe much more, but this is normal. That means in many cases, especially when your watershed is small in the area, maybe you find the whole watershed is like this. Okay? Of course. In other cases, maybe you find your watershed like this. Okay? Because watershed doesn't put itself inside a cell. Okay, so in this case, for example, in this situation, you know by experience that you don't need to open all this file, because you know this file consists of pixels, and that's why analyzing such a data is difficult mission even for good computers. It is difficult to manipulate this data because we are going to analyze this file. We are going to calculate the slopes, the distances, the areas, and accumulate the water. It is really hard work, and that's why it gives you the chance to hit these numbers. These boxes you can modify it. So if you know that watershed is close to here, you can modify these numbers to only import around your watershed. How we can know the boundaries of our watershed? If that saves our time and saves our machine memory, so we need to know this information. The question is how I can know the boundaries around my watershed. I know that this here, for example, is 31.15, while this is how you can know the boundaries of the watershed? What is the easiest method? Exactly. Google Earth is very good and easy way to approximately define the boundaries. Okay. Of course, it doesn't help you to accurately guess the boundaries because Google Earth doesn't display the boundaries of the watershed. You have to guess it. Okay? How we can guess the boundaries of a watershed? Google Earth doesn't show boundaries. Google Earth, if this is a sea, okay, and usually the watersheds flows to the sea. So the watersheds will be something like this. Okay? How we can guess that here is a watershed not they are different. While maybe another watershed looks like this. How we can guess what the satellite images tells us about the boundaries of the watershed? Try, unfortunately, we don't have internet access here, but what satellite image shows you, not the boundaries, it shows you the streams. You can see the streams by Google Earth. So we know the streams, we can see the streams, but we cannot see the boundaries. How we can guess the boundaries? The definition of the watershed. Remember the definition of the watershed. In this watershed, for example, these watersheds as we can see after processing the terrain. Okay? We cannot see the boundaries. We cannot see the boundaries. What we have now? Where is the boundaries between these two watersheds? Imaginarily, there is some boundary. As far as you can see by your naked eyes that this stream is flowing to that direction, while this stream and that stream flowing to that direction, it means there is a kind of dividing line. There is some area here, high in elevation. That's why some streams go in that direction while others go in that direction. Okay? So with your eyes using Google Earth, you will start to see the streams like this, other streams moving like this. So when you're studying the area here, you know that this area is affected and it has studying its flash flood by studying streams till that place. You knowing this information, you can guess the boundaries and download the required files. Okay? Normally, as we said, that DIMs are downloaded. Each file represent 1 degree by 1 degree. It means the DIM files themselves are geographically coordinate system. They are not project. Okay, so you cannot download a DIM file which is projected. It means and any analysis of terrain has to be done over projected files. Why? We said that earlier, previously. Why we have to run all our analysis on projected files, not geographical ones. We said that last time together. Any answers from backside? Hi. I need answers. Why we have to use projected files when we analyzing the terrain? Oh. Yes. Because analysis means calculating length, area, slope, numbers. All these has to be done on something measurable. Okay? So a main step, or maybe one of the earliest steps in working on WMS, after getting the DIM file, is to open it. It is a graphic, then convert it or project it Okay, so you have to know which projection system to convert that geographical file to. WMS reminds us when we add a new geographical file, it reminds us this file is geographic, please convert it now into projected coordinate system. It gives us a window like this. You have to choose what is the current situation and what is the projected coordinate system. Here is an example of from this option or this order is convert that file from geographic WGS 1984 north east to projected system coordinate system UTM WGS 1984 zone 36, which is from 30 degrees east to 36 degrees east, northern hemisphere. This is the meaning of this window. Okay. When we do this step, the WMS will use the old data of the DIM as a geographic and flatten it to be projected. Okay. That's what we will have when we finish the projection. It automatically displays the DIM of the terrain in a contour lines shape format. Okay. It according to where are you working. We here in Egypt usually we use UTM zone 36. Of course, it is different than your situation, your country. That's why you have to search on the internet writing. شكرا جدا جزاك الله خيرا. Search for a map. Search like writing UTM zones. You will see the map with slices. شكرا جدا. And you can guess it from here. Look, it tells us here that UTM zone 36 covers the area between 30 degrees east and 36 degrees east. It means you can look which degrees your country is in, so you can guess which zone. Yes? Okay, let us finish the presentation. Huh? Yes, this is version 7. Your version is different. But the presentation covers the main ideas. So it doesn't matter. Don't follow, don't apply. Just try to understand. This is how DIM files are displayed in WMS after it is read. It displayed as contour lines, small tiny nodes. The first one that it shows the default of the WMS. It shows the high land by blue color, while the lowlands is displayed by reddish color, which is opposite of what we expect. Usually, the printed topographic maps are displayed the brownish or reddish color. This shows the highlands, while the bluish color represents the lowland. That's why usually when you open the file, one of the steps is to reverse the coloring of the DIM. Okay, it makes it understandable, more understandable for your eyes. Secondly, maybe some people doesn't like that complex hairy display of the contour lines, so you can change it into something else. We will show it together, which is not contour but smooth coloring. Okay, so it is these last steps. It has nothing to do with the calculation. It is for visualization, to be friendly visualized. These books, you know, these bottoms, they are different than the ones installed in your machines, but the principle is the same. Each one of those bottoms represent a module. You will have the same bottom, but maybe the shape is different. But each one of those represent a certain module. By module here, we means a component of the WMS. WMS has 1, 2, 3, 6, 8 main modules. Each one to do certain task. For example, one to define some data, another one to make some analysis, another one to make an analysis, but for a special type of the data inputs. Okay, so we have to be aware of these modules to know which one to use at each level. When you start, for example, digitizing something, you have to open one of these modules. The most important modules for hydrology, our course, is the drainage module. And as its name shows us, drainage, so it provides you with toolbars and buttons and functions that helps you manipulate the drainages, which is the watersheds indeed. Drainage here means the watershed. And of course, any hydrological analysis depends on the drainage or the watershed. That's why we have to use that drainage. We usually use also this one. One of the rarest or lowest applied modules are this one and that one, because I think they are analyzing the area two-dimensionally. So it is harder in the run and needs more data. Okay, so that tool, that WMS tool, it contains large number of calculation software. Okay, the same problem could be solved differently using different tools. Okay, the same watershed using the WMS can be analyzed with different software. Okay, so usually we are not interested to put ourselves in the troubles. So two-dimensional modules, because they need more data and more effort, usually less people are interested to solve using them if they can use an easier alternative. Okay. When you click on when you activate the drainage module, these are the even the menu bars are changing according to which modules is selected. Okay, so not only the toolbars are changing, but even the menus. Okay. In this case, in this snapshot, the drainage module is selected, so that the menu is displayed. When you check another one, maybe you will not see this menu at all. Okay, this step, compute to base flow data, is every one of you. We will apply this step today, inshallah. I think you did it last time. You used this step. Huh? Okay. Let me refresh it in your mind. Starting by the DEM file, which is just a matrix of numbers, downloadable file, finishing by a watershed and streams. Okay. This process, usually when you try to do it using GIS tools, it takes many steps. You have to do many intermediate outputs till you find yourself have a delineated watershed with delineated streams. Okay, this is usually happens. You have to do many steps using QGIS or ArcGIS till you find yourself have the watershed. But in WMS, it's just one step. When you run compute to base, it reads the DEM file and it does most of the work for you. Finishes with stream network all over the DEM area. It gives you a stream over all the area. Okay, so it represents big part of the task done just by one click compared with the GIS software. Okay. Tobaz itself was, I think, an independent software or independent tool, but they have embedded it into the WMS. So usually, when you work with just such a complex solving tool, don't think it is that huge. In many cases, it is a combination of simpler tools. Okay, so Tobaz in long time ago, it was an independent tool. You can just use it to analyze the terrain file to produce the stream network. Okay. As a way of saving your results or outputs, when you run the Tobaz, it asks you, do you like me to save the outputs for you? When you usually it is all selected. It means just by running the Tobaz, you will have file for the elevation, file for the flow direction, file the flow accumulation, and report file. Usually, each one of those it has an independent step if you are using another GIS tool. It's just funny somehow that when you are using the WMS, you have many times to define the unit system. You define it when you start by the projection definition. Then when you make the tobaz, you have to, I am using meter system. Don't forget, calculate everything in meters. Okay? This is the window that appears when you run the tobaz. What is going on here is just the display of the processing, okay, and gives you if there is a warning message or finishing message, everything is displayed here because this is a run. This when you just click to pass, okay, it is a process, complex processes indeed. Here is time used for the process, and here is this bottom will stay aboard as long as the processing is going on. When it is finished, this word will be closed. When you see this close, it means it finished the tobaz process. Now it is finished. That's why it became closed. As we can see here, it is written beginning pre-processing, like beginning and finish messages. I hope you can notice from the screen that in addition to the contour lines, now there is a lot of blue small lines. These are the streams. Those are resultant of finishing the tobaz running. Okay, this is the output. So now you have a network of streams over the dim area. Okay, اتفضل. Yes, yes. But this is not good because these streams cover everywhere in the DIM. So if you took that shape file, it means you will have in each pixel a stream. It is not useful at all because what is useful for you is you need a shape file for the streams that forms the watershed. Some tools for managing the display like move, zoom, rotate. As you can see now, the streams are much more clear and they are very logic because you know if these streams are not displayed, you see the contour lines. They are telling us if someone of you has some experience with reading maps. These contour lines tells us there is a stream here. Can you notice that? So the streams, we have the stream network from the beginning till the outlet here. Here's a good answer for your question. Our friend Mus'ab asked, can I take the whole streams? Let me tell you something. Tubaz calculate the water path in every pixel. But what you see here is just display for the important streams. Okay? But if you take out all the streams, you will have nothing to be used for. But in this step, we are going to define the area we are interested in, which is called the outlet. It is the point where we need to calculate the accumulation of the water of the flood at. So when we define the outlet, the WMS started to delineate, or in other words, find the areas that feeds this point with the water. Okay, that definition is the watershed itself. Okay, so if this is a limb, we run the tubas. So for each pixel, let us zoom this pixel. If we zoom this pixel, what is here is either one of those, or what are those? Each, God bless you. Each one of those is a possibility for the flow direction. Okay? Because in each pixel, the flow will go that direction or that one, that direction or that one, that direction, that one, that direction, that one. These are the all possibilities. So by running the tubas, you will have in each pixel a number represents the direction of the flow, according to the difference in elevation between each pixel and the surrounding one. Okay? So each pixel is surrounded by 9 pixels. According to the difference in elevation between this one and the surrounding ones, it defines the flow direction. So by tubas, you will have for the whole 10 directions. You are aware of that? Have you studied this before? Is it yes or no? No. Oh, no. No. Okay. So, what is a stream? I need two answers. The physical answer, which is geographic answer, and the numerical answer. Machines like WMS doesn't understand a stream. It has it has another definition of the stream. For us, what is a stream? Stream is part of the land. That part is lower in elevation than the surrounding area, so the water flows to it. And when the water started to accumulate in this channel, it started to move either in that direction or that one according to the slope. So when we take a cut, it is like this, filled of water, the water is going in that direction. This is the stream as we understand it from the geography. But how the WMS or any other tool understand what is a stream? For that tool, stream is, if this is a dam, okay? Let us zoom one. Just take a small part of the dam and study it as a matrix of elevations. Each one has an elevation, okay? This is the definition of the dam. The dam is a matrix. Each pixel has a number. That number represents the elevation. So dam is a representation of the land surface. Okay? So by analyzing, which is called tubas, by analyzing the dam, it means convert this one, which is elevations. Let us put any number, no? 90 meters. Okay, these numbers represent the efficiency. What does it mean run the tubes? What does it mean run or run tubes means, hey, WMS, please find me the streams. Okay, this is running the tubes. So what we can do here is running the tubes means it is completely mathematical calculations. Okay, for each pixel of those, calculate the shortest path by means. Look to this elevation and the surrounding ones. This is 90, 87, 70, 100. So at this corner, what is the direction of the water? If a point of water is here, what is how it will go? We know nothing in these three directions. We know nothing here. All what we know is in this area. If a drop of water is here, how it will go? It has three possibilities. It has three possibilities. Either to go from 90 to 87, or to 70, or to 101. What is the expected flow direction? Raise your voice, please. 70. This is the highest slope. And from 97, exactly. And from 70, have you noticed? Notice now. So from this point, it will start to accumulate water from many places. Okay? But to be honest with you, that water, this pixel will be something like a lake. Okay? But let us continue. From 66, it will go to here. No flow will be from between these, yes. But from 77, it goes here also. From here, it goes there. From here, it goes there. Okay? So, the same. So now, if we continue looking for pixels here, we expect that water is going in that direction. So, from this point, a stream started to be formed. The numbers, if I assume them proper than this, the stream will be clearer. Okay? You will start to have the point? It's something like this. Each one of those is a flow direction. So stream, by the WMS terms, means a series of flow direction values that finally ends with the output. So it could be guessed reversely from the outlet point and find the steepest path to the highest till ends with the place. It will not go further. For example, something like this. Okay? Or here, for example, if you arrive to peak elevation, it will not continue. Okay? So these streams came from something like that. Okay? It is completely mathematical equations. 10 quarter after 10. Let us take a break for a few minutes.